I'm going to focus on the problem that I think has received the most, the single problem that I think has received the most attention in the database community, which is batch query answering. And I'll try to survey the results as they stand now. So the problem of batch or non-interactive query answering is given a fixed set of queries. We want to answer them, and we have one interaction with the database to do that. So it's worth taking a moment to think about where these queries come from. So as Moritz suggested, there may be a more complex data analysis task that we want to carry out, and we decompose that into a set of simple queries that we try to answer. There may be multiple users who want to interact with the database, and if we don't trust them that they won't collude, we need to hold them to the same privacy budget. And if we have one interaction with the database, we might want to lump those queries together into a big set. And there may also be uncertainty about what the analyst actually wants to know. And so they overestimate what they want to know about the database and try to answer all those queries at once. So I usually think of this workload, which is what I'll call it throughout the talk, as a potentially messy, not very well structured set of queries that we want to answer. The goal is to release answers to queries under epsilon or epsilon delta differential privacy. I'll talk a bit about both. And we will focus on the set of queries that Moritz described, actually linear counting queries. So these include spatial queries and multidimensional range queries and marginals and lots of practical stuff. I'll describe those in a moment. So I've divided the talk into two basic approaches and that have some stuff in common. So they both use one of the standard mechanisms as a kind of subroutine, either the Laplace or Gaussian mechanism, and they try to improve upon that by doing something clever. And the clever thing that they try to do is basically ask questions differentially privately that are different than the workload. Okay? So the first approach are the techniques that are workload aware. So normally what you would do, you would apply a Gaussian or a Laplace mechanism, you'd take a workload, you'd submit it to the server, and you'd get the noisy answers back. So the difference with approach one is that we will in some way decompose the workload into a set of observations, a different set of queries, and submit those to the standard mechanism and get the answers back. Although these are not the answers that we want, because we want the answers to the workload queries. So then we have to derive the answers that we want from them. Okay, so we need to select these observations. So this is one of the potential challenges of approach one is how do we select the observations? Then we apply the standard mechanism. That's easy. And then we have to derive the answers from the workload queries, and we might have to think a little bit about how to do that the right way. And the key principle behind the workload-aware mechanisms, this class of mechanisms that this distinction I'm making, is that the selection of the observations is done only by thinking carefully about the workload itself and not thinking about the data. Okay? So there's been a bunch of work that can be seen as an instance of this approach one. Okay? And you're going to learn about, if you haven't read these papers, then hopefully after this talk you won't have to read all these papers. They may have targeted different classes of queries. Some focus on marginals, some focus on range queries, and some do focus on the more general class of linear queries. And they have different ways of selecting the observations. And I will make a distinction between one category of work. They sort of have a fixed set of observations. They've observed that for this type of workload, these observations are good, and so we'll use those. And then there are some that are more adaptive or optimized. They say, well, let's just take the workload, analyze it, and find out what the observations should be. What are the good observations? Okay, so we'll come back to this. Now, approach two, I'm calling the data-aware algorithms, are different, a little bit different. So we start with the workload. And now, in order to decide on the observations that we want to make privately, we are going to do some interactions with the database, some tests, and look at the data a little bit in some way, get the noisy results of that, then select the observations, submit them to the database, get those answers back, and then eventually derive the answers to the queries that we care about, the workload queries. Okay? So there's two interactions with the database, so obviously both of those need to be private. And one of the challenges in this category of work is to balance these interactions that are, to some extent just to select the observations and then use the observations to learn about the query answers. Okay, so here we have this testing phase to select the observations, and then the other phases are the same. Okay, so some of the recent work in this category, again, focuses on certain workloads, and we'll see the different techniques here. So the key thing is that the observations selected may use the data, may be adaptive. And in some sense, this should be more powerful because we can exploit properties of the data. And I will mention Hart's, the recent work by Hart et al. At the end, and I won't have to say much about it because Moritz did such a nice job of describing it. Okay, so I'll first start with some preliminaries, and then I'll talk about the workload-aware techniques and go on from there. So Moritz mentioned this, but we do have to go from a database to a vector. And this is a very awkward thing to do for a database person because it is really a very poor representation of a database, but we have to do it. So we have to take a relational database, which is records, and with multiple columns, these are it may be multiple dimensions, and we have to turn it into a vector. And so in this example, we might be asking queries on gender and grade, and so and if we have a continuous domain, we have to bucket. In practice, we have to bucket. So in this case, we look at males and females and different grades, and we get 10 counts out, and we represent our database as a set of counts. If we just want to ask queries on one dimension of the database, we would construct a different frequency vector. So I'm going to use this vector x1 through xn, and it'll be, unfortunately, inconsistent notation because I'll use little n as the size of this vector. And I'll refer to this as the domain. And obviously, in the worst case, it can be very large because you have the product of the domain sizes if the data is discrete. But in practice, this is obvious, but it has actually implications in practice. You can construct this frequency vector so that it supports only the queries that you care about by sort of compressing it. And that can really, that can reduce the size of the vector for one thing and improve efficiency, but it can also sometimes have impact on some of these techniques. Okay, so a linear counting query is just a linear combination of this x vector. We can represent that as a row vector of coefficients, and then we can compute the query by the dot product of w with x. And then when we talk about workload sets of linear queries, we can represent those as a matrix. Every row in the matrix is a query, and then we can compute the list of results that we want as the matrix w times x. And so I mentioned that these linear queries can support a bunch of things that we want to do in practice. In particular, we can ask one-dimensional range queries. These are intervals. And we can also ask if the weird thing is that it won't be obvious necessarily whether this x vector represents multi-dimensional data or whether it's actually representing single-dimensional data. That's sort of hidden in the representation of the database, but it's there in the background. And I'll sort of jump between some work only applies to one-dimensional data and so forth. But at any rate, we have one-dimensional range queries, intervals, we have marginals, contingency tables. There we select certain dimensions and we enumerate their values, and then we aggregate over all the unmentioned dimensions. And so a marginal or a contingency table is a lot of linear counting queries. All of the one-dimensional range queries and the marginals are all instances of k-dimensional queries, which are like axis-aligned rectangles and high dimensions. And all of those are instances of predicate counting queries where the coefficients are just 0 or 1. But in fact, we can support a slightly more general class of linear counting queries where we have arbitrary coefficients. I mean, and despite the name, linear counting queries, these can express things that aren't normally thought of as counting queries, like averages. You could compute the average by weighting the coefficients. Okay, so we'll use differential privacy. I won't spend any time on this. We'll use the standard Laplace mechanism and the Gaussian mechanism. When I say apply the Laplace or Gaussian mechanism, what I typically mean is the multi-query version of it, where we have multiple questions, we apply the Laplace mechanism, and we add independent noise in each component to each query. And we'll also mention the exponential mechanism. And I assume that everyone here has this background. Okay, so if we use the matrix form for our workloads, then we can very conveniently represent the sensitivity of a query matrix of a workload as a property of the matrix. So if the key property of this X vector is that if a record is added or deleted, then one count changes by exactly 1. And so if that count changes, then when we multiply the first query, which is a row, when we multiply that by x, then it's going to change the answer y1 by an amount equal to the coefficient in that coordinate. And then it's going to change y2 by the coefficient in that coordinate, and so on. So the sensitivity is of this query matrix. The L1 sensitivity is the maximum L1 norm of the columns of this matrix. And similarly, the L2 sensitivity is the maximum L2 norm of the columns. Okay, all clear. So let's dive into approach 1. I'll start with the variant of the techniques that just sort of like propose fixed sets of observations that work for a given workload. And I'll motivate this by a class that's, of queries that has received a lot of attention in the database work, and that's the set of all range queries. So simultaneously, all at once, we would like to produce answers to all range queries over a data set that's one-dimensional, let's say. So this is all queries W such that W equals the sum from xi to xj, so there's depending on the order. So there's a lot of these queries. There's n squared queries, and here if our database has size 4, then there's 10 queries in this case. So if we apply this to real numbers, we get some query answers. So we get 10 numbers out, which is what we want. All right, so I'm going to go through a few methods just to motivate this and start off slowly. So the first thing you can do is apply the basic Laplace mechanism to this workload consisting of all the range queries. So the problem with this is that the sensitivity of this workload is kind of high. Okay, so you scale by Laplace noise, you get the output. Okay, the reason I'm showing you the numbers is because I want to point out one inconvenient byproduct here, which is that you get your 10 answers out, but they're inconsistent. So this is an estimate for a noisy estimate of x1, and this is a noisy estimate of x2. But if you add these together, your noisy estimates, and ask whether it's equal to the estimate for this query, which is the sum, they're not equal. Okay, so that's a slightly annoying problem. But the real problem here is that the sensitivity is high. Okay, as a function of n, the sensitivity is going to be order n squared, and then you're going to add an enormous amount of noise to answer these queries. Okay, so method 2 to answer the range queries. We'll use the Laplace mechanism instead to answer, to get noisy estimates for each of the individual vector coordinates. Okay, so now the observations, this is really a different set of observations that we're going to use. We will, and this observations has the nice property that the sensitivity is very low, and we apply Laplace noise and we get our private output. Now, this is not the answer to the workload queries that we want, so we need to reconstruct the derived the workload query answers. And that's really obvious here because this is a noisy estimate of x1, this is a noisy estimate of x2, so we know naturally how to do that. We just sum things up to get the range queries. So this works well in the sense that the observations we submit have low sensitivity. The drawback is that when you sum up large ranges, because you've added independent noise to each component, the noise accumulates and you get poor performance on the large ranges. Okay, so method 3 proposes a different set of observations that form a hierarchy. So we will ask the sum of all the values in our x vector, and then we'll decompose it into 2 halves and ask for the first half and the second half, and then we'll ask for the individual components. So the sensitivity of this observation matrix, or these observations, is 3. In general, it's log n plus 1. And then we get 7 answers out. but we have to derive the workload answers. Okay, so it's a little bit trickier here. Let's consider deriving estimates for the range query x2 and x3. So we want just the sum of x2 and x3. And there's more than one way to do that. I mean, I could just take the noisy estimate for x2 and the noisy estimate for x3 and sum them. That's a valid estimate. But I could do other things too. I could take z2, which is the estimate of x1 plus x2, and I could subtract off z4 and then add z6. That's another valid estimate. And I could do other things too, and then the proper way to combine this and derive a principled estimate is to use the ordinary least squares estimator for this query. So that's what was proposed by us, in fact. And so we would answer this range query by this complex linear combination of all of the noisy estimates that we have. They all play a role in estimating this, and that reduces the error a bit. Okay, so because the sensitivity is logarithmic, even when n gets big, we get pretty good performance of answering all the range queries. So this is on a domain size of 1024 with epsilon 0.1. If you plot the error as a function of the size of the range query, so we got small range queries and big range queries. If you use the noisy counts, then the error just grows with the size of the range. And here it's dampened quite a bit. I mean, you pay a little bit of a price on the short ranges because you have higher sensitivity. But on the big ranges, it pays off. Okay, so I'm going to make this all more formal. This is kind of the motivating example, and I think a lot of things will be clear. So I just want to show experimentally the impact of this. Now, there's another approach is to use some observations based on a wavelet matrix, or wavelet observation. So the Haar wavelet, in a very small example of it, is to ask for the sum and then decompose the domain and ask for the difference between this half of the domain and this half of the domain, and then decompose again and ask for the difference between x1 and x2 and x3 and x4. Okay? So the sensitivity of this is exactly the same as the previous matrix. It's log n plus 1. And here we get our noisy observations, and then we have to reconstruct the range queries again. And there's a way to do this. With the reconstruction coefficients of the wavelet matrix, I mean, it turns out it's consistent with minimizing the L2 error. Okay, so in this case, you would again use a combination of your noisy estimates, and you don't have the consistency problem here, but you still want to use all the evidence that you have to get the best estimate. Okay, so the performance of this is very similar. So the hierarchical is the red, the wavelet is the green. Actually, the hierarchical, you could play around with the branching factor and you can lower error a little bit because you lower sensitivity. But ultimately, these two things are the same. And the hierarchical came from our group, and the wavelet stuff came from Johannes Gerke's group. And we were really trying to figure out, to be honest, which was better. Did ours beat theirs or did theirs beat us? And and then we discovered that there's a sort of way to generalize this, which I'm gonna get at. So what I've shown you so far is that there's different observations that you could use to derive answers to the same set of workload queries, the range queries. You could use noisy counts, or you could use these two sets of observations. This has the advantage of very low sensitivity, but large ranges are estimated badly, and this has pretty low sensitivity, logarithmic, and you can bound the error that you're going to get. It's easy to see that actually the sensitivity is logarithmic in n, and so then with the scalable Laplace noise squares that, and then every range query can be constructed by at most logarithmic estimates. Okay. Now we're actually doing something. The least square stuff makes that more complicated. That bound comes from just reconstructing the estimates any way you want. The least square stuff reduces the error a bit, but this is a bound on the error. Okay, so there are other instances of the same paradigm of using a different set of observations to answer a workload of queries. One is by Kermode recently suggested that his focus was on spatial queries, so two-dimensional range queries. The motivation is like location data and stuff like that. And he did something similar to the hierarchical structure, but in 2 dimensions. It's a quad tree, and you divide the domain. And he also observed that it helps you if you make the leaves of this tree more accurate than the root, so you can scale the epsilon that you use at each level. It's, in his formulation, it's uniform by levels, but it's scaled level by level geometrically. And another instance of this is actually the Fourier basis technique to answer marginals. So it helps a lot if instead of actually submitting a set of marginals, lower order marginals to the Laplace mechanism, you actually submit these Fourier basis queries and then compute the marginals from them. Okay. So parenthetically, I mean, some of you may have seen this work in the form the Fourier basis queries and the wavelet, they're both transforms. And so another interpretation of all the stuff that's going on here is that you're going to take your database and transform it to a new domain, represent your workload of queries in that domain, compute the sensitivity, and then transform back. And that's equivalent. It's just I prefer to present it this way because I think it's a bit more general. And not everything that we consider is a transformation. Those hierarchical trees are not transformations, so it sort of breaks down. Okay, so these techniques are interesting, and the way I see them is that they each have an insight that for a given workload, this set of observations is good, works well. Okay, but it leaves some questions open, like are these observations actually the best ones for those workloads? And furthermore, this is only a fairly restricted set of workloads. I mean, this was the workload of all range queries. What if I want to randomly select some range queries or only care about a certain part of the domain or certain kind of ad hoc subset of workload of range queries? Then this may not be the best way to go. And we'd like to be able to customize the observations to the actual workload we care about. So the next techniques try to do that. So first, let me give you some background. So let's look at the matrix. Let's look at the Laplace mechanism in matrix notation first, because I'm going to compare it with a generalization of it. So here we have our a randomized algorithm which takes W and X, the database, W the workload. We compute the true answers, WX, and then we add noise. Right, so B is a vector of independent samples from the Laplace with scale 1, and then I'll multiply that by this parameter to scale up the noise appropriately. So everyone's familiar with this. The error is constant for every query, so it's, there's no analysis needed. So the justification for what we call the matrix mechanism is the following. We're going to select some observations, and we'll talk in a moment about how to do that. And for now, and we'll represent them as a matrix, the observation matrix A, and we'll assume, for simplicity of the discussion, that it's full rank. It really just needs to be capable of representing the workload. But let's just assume for now it's full rank. And the range queries is a full rank workload. Anyway, so we'll stick with that analogy. We'll apply the Laplace mechanism to get answers to the queries in A. So that looks like this. Okay, this was the Laplace mechanism in matrix notation. I get the Z out, the noisy answers, a vector of numbers. Then I need to do the derivation process. I really want to do this by computing an estimate of the database, X bar, using the answers that I got in Z. Okay, I'll do that by computing the estimate that minimizes the squared error. So Leela, I think this is what you were trying to ask me. Sorry for being unclear. So that's my choice, okay, that I'm trying to minimize that. The solution is the ordinary least squares estimator, where X bar is set equal to the pseudo inverse of A times Z. Okay, if A happens to be invertible, then it's just the inverse, but it may not be. And I mean, there is a basis for this estimator. It's unbiased, and it has the least variance amongst all linear unbiased estimators. So that was our justification for considering this at first. And then, now that I have, you could think of this as a synthetic database, a noisy version of the true database. Then I'll just compute the workload queries from it. Okay, and that's an algorithm. And we call that the matrix mechanism, and we can reformulate that whole process in this formula. So now we have a randomized algorithm that operates on the workload and the database, but it's instantiated with this observation matrix A. So you got to pick that. Once you do that, what happens is you compute the true answers and you add noise. Just like the Laplace mechanism, except the noise is scaled in a funny way. First of all, it's scaled to the sensitivity of the observations, not the workload. And then it's transformed by this function of W and A. Yes?
So you're trying to reconstruct the database as opposed to the answers on the workload. In the previous slide, you were
Yes.
trying to come up with the best estimate of X as opposed to the best estimate of WX. Why is that?
Well, that's a good question. So for one thing, this is.
I guess it'll give you consistency most likely.
Yeah, I mean.
If X is non-negative, I don't know if you're guaranteed that X is non-negative.
No, it doesn't guarantee that it's non-negative. So, but it does give you a form of consistency with respect to the workload queries. They're all internally consistent. They're not necessarily non-negative. Yeah. So I'm not sure if there's another estimation process that would be preferable for W.
I guess I was going to ask the same question. So maybe you could argue under some circumstances that this is the best least squares estimator for WZ also, but then you'd probably need some additional assumptions on W, like it's spherical kind of thing.
Yeah.
Like sometimes it seems like this is making your life harder, and that privacy is trying to protect X, and the hope is that even without knowing X too exactly, WX is somehow easier to compute.
Well, okay, but so I don't know, but we're going to compute A by looking carefully at W. So, I mean, we're not trying to construct an X here that's good for everything. We're trying to construct something that's good for W, and A reflects that. A reflects should reflect the right observations that help you answer W. And the reason it's necessary is that W is messy, and it's got redundancy and high sensitivity and stuff that the computation of A is designed to kind of correct in some sense. Because at the root of it, we're using a simplistic mechanism as a subroutine that adds independent noise. So the A queries are answered with independent noise, and W doesn't want that in some sense. Okay. So this is the mechanism. We instantiate with A, we compute the true answer, we scale by sensitivity of A instead of W, which is going to be much lower, and then we transform the noise vector. And you can compare that with this, with the Laplace mechanism. So the techniques that we saw are instances of this. Okay, so now, I mean, the problem, the burden you bear when you use this algorithm is that you have to come up with A. So it's interesting to note that even if you do no work, if you set A to W, you might say, well, do I recover exactly the Laplace mechanism? Actually, you never do worse, but you can actually do better, because you will sort of combine evidence from the noisy answers to the workload queries through the linear regression process, and you may improve some things. But ultimately, you want to do better. So you can set A to the identity matrix. That's the noisy counts sort of method I talked about. You could set it to the wavelet or a tree structure type thing. This tends to be good for range queries or multidimensional range queries, or the Fourier basis for marginals. Okay, but ultimately, we're looking for a technique to adapt to compute A automatically. So, and one of the questions that motivate us for that is obviously, well, are those observation matrices optimal? And it turns out that they're not. So an example is for wavelet. So it turns out that the sensitivity of this matrix is 3, the wavelet, and it's equivalent in that it offers exactly the same error on every single query that comes out of the mechanism as this matrix, and you'll have to take my word for it about that. But once you look at this, you might observe that we're asking the same query twice. And that's usually not a good thing to do under the Laplace mechanism. So you can actually kind of compress this and weight these queries by a factor, and you reduce the sensitivity of that, and now these observations are much better than these. So for every query, the error is lower if you use those observations. So in some sense, this suggests that you should throw wavelet out and never use this as an observation matrix because it's dominated by another matrix. Okay? We'd like to avoid that kind of thing, but in addition, we want to know, I mean, that's one problem. We should never consider observation matrices that are dominated by others. But in addition, we want this adaptivity to fit them to the workloads that we care about. So to do that, we can look at the error. There's a closed form expression for the error of any workload query when we use this mechanism. Okay, so it depends on 2 over epsilon squared, square of the sensitivity of the observation matrix, and this thing which looks a little bit like a covariance matrix with respect to A. All right? And if we want to look at the total workload, which is a convenient thing to try to minimize, then you can write it like this, where the W's become big W's, and we have the trace here. Okay? So an important byproduct of this is that all the techniques have error rates that are independent of the data. The database doesn't appear here, right? So that's clear. And that's a property of all this class of algorithms, these workload-aware ones. They're all independent of the data. And that's both a bug and a feature, and we'll talk about that. Okay, so now we'd like to, given a workload W, find the observation matrix that minimizes the total error. Oh, yeah, Sylvia?
I think actually the last line there was the question I was
Yeah.
going to ask. So is that the sum of the squares of the...
Yes.
Or the sum of those errors?
It's the sum of the per query squared error values. Yeah. Yeah, that comes out when you take the trace. So we're given a workload, and we want to try to compute A. And this is a hard optimization problem. And other people have tried sub-problems. So there is, outside of the work of the matrix mechanism, in the space of just marginals, there was an attempt by Ding to optimize. Basically, you're given a workload of data cube queries, and the optimization problem is find the best set of observations consisting only of data cube queries to answer those. And everything, the same machinery applies, and they use a set cover algorithm to solve that optimization problem. I won't say more about that. The other techniques for optimizing fall into the setting of the matrix mechanism. So in our original work on this, we encoded this optimization problem as using semi-definite programs, but the solutions were not efficient. So you can minimize total error under, and here it's different with L1 and L2. So actually you can do the whole machinery of the matrix mechanism in epsilon differential privacy or epsilon delta differential privacy, use a different norm, and everything works exactly the same. All the machinery works the same. The minimization problem is actually easier if you use epsilon delta differential privacy, and one intuition for that is that when this is the L2 sensitivity, then this is a property of ATA. I mean, it's determined by ATA, whereas L1 it's not. So you can find a good ATA, but then you still have the problem of finding there's many A's that will give you the same ATA, and you have the problem of minimizing the sensitivity, keeping ATA constant, and even that optimization problem is quite hard, as far as we know. So our best solution, I mean, we're looking for things that we can actually run on real data sets, was n to the 8th to solve these STPs. Recently, in this year's VLDB, some other authors came up with a relaxation of this problem, which makes it much more efficient in the L1 case and seems to produce good results. So there's hope that we could actually come up with good strategy observation matrices A in the L1 case, and we've come up with a sort of approximate optimization problem that is more efficient in the L2 case. And there we choose a basis. So we use the eigenvectors of the workload, and we just scale them. And we use that as our strategy. And we optimize only the weights on the eigenvectors of the, and that seems to work well in practice. Yes?
So I think that was my question. Isn't sort of the top case in the vectors, by definition, the least square subspace for the query set? If I I have a set of queries and I want the dk vectors that minimize the L2 error for all the queries, then that would be the top casing the vectors.
Geez, I don't know the answer to that question. I don't know enough about the theory. But, I mean, I know that what we found was...
I think this might be your algorithm.
We have this other term, though, which is the magnitude of the entries, the sensitivity.
Column sensitivity.
But because if you talk about epsilon delta, it's all the
Right,
noise is
epsilon
rotationally
delta, I'm not
invariant,
sure.
and so it doesn't matter what the.
So actually it matters for the way you put on the eigenvectors. So intuitively, it seems like you can choose the top k. Even if you choose the top k eigenvectors, you still need to know what the weight you put on. So how you distribute your sensitivity budget on each of your queries.
Right, but this is privacy budgeting. So modular privacy budgeting, right? It's, you just want the smallest numbers. It's just the case in the vector.
I'm not quite sure.
Anyway, we can take that offline.
Okay. That Chow is my graduate student, and this is his thesis work, so he's qualified to help answer those questions. But so I mean, I think in practice, Moritz, I think what we found is that our motivation was to simplify the optimization problem. So now you're only looking for n weights, and I don't think we had a theoretical justification for choosing the eigenvalues, the eigenvectors as the basis, but we did verify that empirically it's better than other. I mean, you could try, well, maybe the wavelet is a good universal basis or something like that, and the eigenvectors are better. Okay. So the point is that we have reasonably efficient methods for computing this A matrix given a workload and customizing these observations to what we want to know. I wanted to try to give you some sense, some sort of back of the envelope sense of what this means in practice if we try to, because all these algorithms are running on real or realistic data sets, and to convince you that, these techniques have significant impact on, if you look at the average error, per query error of answering a workload of queries, then using something like wavelet or these hierarchical structures will reduce the per query error by a factor of 2 to 4, roughly. And the benefit of optimizing your observations is also significant. So you can reduce the error by 2 to 3 times as compared with using sort of a fixed observation, for randomly generated workloads or something like that. And even more under epsilon delta differential privacy. Of course, these are error improvements without any cost to privacy, so these are very significant, and in practice, we really want to achieve these. So those ratios are based on root mean squared error, because I don't want to distort the ratios of the error by reporting everything in squared error. And the other thing is that it's easy to look at these techniques and evaluate them, because if you do experiments and you look at numbers, they're independent of the data set, and independent of and relative comparisons are independent of the privacy parameters. So it's nice in that sense. There's one asterisk there, is that actually this technique, this relaxation of the optimization problem, introduces a subtle dependence on the data that I won't try to explain. Okay, so we did prove a lower bound on sort of the optimization problems don't tell us well how low can the what quality of results will we get when we solve these optimization problems? And we do have one result on that, which is tight for epsilon delta differential privacy, and shows that the minimum error, the minimum total error of the matrix mechanism is going to be at least this function of the singular values. Okay, a function of the singular values. It's not tight for epsilon differential privacy, and I think we know that there's a gap there. But our optimization problem is finding in practice solutions that are very, very close to the lower bound. So we know at least we can use it at least for that, and know that with respect to epsilon delta differential privacy, especially for things like marginals, we can achieve, essentially effectively achieve the lower bound. Okay, So in terms of efficiency for this class of mechanisms, they're generally quite efficient. So if you do a kind of naive implementation of Laplace or a Gaussian mechanism, you're going to look at running time, which is the size of the workload times n, the domain size. Now, the costly part is selecting the observations, which might be n to the fourth. Then you apply the standard mechanism and you derive answers. The one point I want to make here is that some of the work in this area has shown that if your observations have a special form, the least squares can be carried out more efficiently. If it looks like a hierarchy, a tree, or a DAG, then you can do the least squares more efficiently than the matrix manipulation, and in practice that can sometimes be helpful. The other thing to note is that if we fix the workload and we've already optimized, done the optimization and chosen an A, then we can implement the mechanism very efficiently. Okay, so if you have a workload that reoccurs, then you can cache the observation matrix that works well, that is close to optimal, and keep it around and use it whenever somebody needs to apply it to the workload. Okay, so that summarizes this class of work. We've got all these different techniques. Some are fixed associations between observations and workloads, and others are adapting the set of observations to the workload. Okay, so I'm going to go on. Any last questions about that? Okay. Well, before I go on, I'm going to summarize. So the independence of the data makes error analysis easy. The error rates are, like in the Laplace mechanism, publishable because they're not sensitive. And in some cases, it improves efficiency to have this data independence because you don't have to recompute things. This computational dependence on the domain size is inconvenient. So as you know, database folks don't like to represent their databases like the vectors, and we would hope in the absence of privacy, I mean, we wouldn't hope, we would have much more efficient query evaluation techniques. So this is, I don't know if this is sort of unavoidable, or, but it does seem annoying. All of these techniques are going to have dependence on epsilon of, at least in the L1 case, of epsilon 1 over epsilon squared. I mean, no, in both cases, over 1 over epsilon squared. And we'll see some techniques that avoid that. For some workloads, there's no set of observations that can help much. All right, so there are limits to this. I mean, essentially, by computing this observation matrix, you're exploiting some correlations in the workload. And if you have all predicate queries in a workload, you can't improve on that by finding another set of observations that's going to lower error much. So there's limits to what's being exploited here. Some open questions are, why do least squares, standard least squares as your inference method? One obvious thing that came up is that the answers may not be non-negative. They have other form of consistency, but they're not necessarily non-negative. So you could do non-negative least squares, which is something we've played around with, and in some cases this actually reduces error, but it makes those nice closed form error formulas and also the optimization problems much trickier to carry out. And we've talked to some statisticians who told us that there doesn't seem to be a way to analyze the error of non-negative least squares in general. The people we talked to said they simulate to do that. We don't know the relationship with sort of universal lower bounds. Our lower bound is a lower bound over all of the observation matrices you could pick. It's not saying that all differentially private mechanisms. So that's also, there's a gap there that we need to understand. Yes?
A question. Can I go back to the previous slide? So here it said R dependence depends on 1 over n square. Why is there a limit? Is that because you are using Laplace mechanism?
Yeah. I mean, essentially, it follows from, it's inherited because we're using the Laplace and Gaussian mechanism as a subroutine. Yeah, so I don't think we can escape that.
Squared error.
Yeah, for squared error. For squared
so
error. Yeah.
Sort of on the scale of the answers, the dependency is 1 over epsilon, right?
Yeah. Yeah.
I want to mention that recently we did some work on design some better mechanism, and we can improve the bounds over 1 over n square.
Okay. Okay, great.
So, but one of the questions is whether the mechanism depends on database or not. So
It
we
depends
will
on the database.
depend on database?
Yeah, I will give you a student talk tomorrow too, so if you're interested.
Okay. Okay, great. Yes.
It may also be worth pointing out that there's a theorem that says that if you want to work for all databases, then this assumption that the error is independent of the data is without loss of generality up to constants.
Okay.
So
Okay. Yeah. Good. Okay, so now I'll move on to the data aware, and luckily I have less to say about that because how much time do
12 minutes.
Okay, I'll try to get through this. So here, recall that this is approach 2. So these are data aware techniques where we are going to, in some sense, select our observations with some knowledge of the data. Okay, and one of the challenges here is to balance what we learn about the data in order to select observations and the observations themselves that we use to answer queries. And even that distinction can come into question. But most of these techniques, in most of the techniques I'll present, there is a distinction between those two phases. And it's not clear that the information is being used optimally. But we'll talk about that. So one of the basic intuitions here is that you'd like to use the data to detect in some way when you should spend your privacy budget to learn more about the data. So for example, if the gray is the true database and you've done some measurements, you've done some observations and used your privacy budget to learn, for example, that the sum of x1 plus x2 plus x3 is this value, then what you would typically do is assume that x1 and x2, that there's, you don't have information, but you're going to assume uniformity inside that domain. Okay? Now, if you do that, then you might say that you know enough about this portion of the domain, x6 through x10, and that you don't need to learn much more about that portion of the domain. You should sort of leave it alone. Okay? But x4 and x5, there's actually, in the true data, a big discrepancy. If you assume uniformity here, you're going to way overestimate x4, and you'll get x5 roughly right. And you may want to spend more of your budget there, and you need to balance between sort of finding out when I need more information and so on. And this introduces two kinds of error. So I mean, in the former class of work, we really just had error that results from perturbation. And we never try to, it may not have been clear from the discussion, but we would never try to estimate a query answer by sort of dividing a range where we didn't have any information. We would always ask if our workload needed to compute from, using an xi, we would have some estimate for that xi. So here we may have approximation error. Okay, so one recent technique is I'll call a data-aware histogram. So the insight here is that if you're working in one dimension and you're trying to decide which histogram to compute privately, then you might want to do some accesses with the database to decide on the histogram. So in database research, we've studied this problem a lot. And there's a notion, I mean, maybe it's outside of databases too, but we use histograms in database systems in order to compute statistics over the database and use them in query for the query optimizer. And we can tolerate approximation error. And in fact, what we really want is a compressed version of the histogram. So we want a few bins, a small number of bins in our histogram that approximates the data well. And so one way of doing that is computing a variance optimal histogram for a given set of bins k. And there are methods for this. So what these authors did was try to compute a variance optimal histogram privately first, in a first step of the algorithm. And so they used the exponential mechanism to basically randomize the boundaries of the bins. And they use a portion of their privacy budget to do that. Once they do that, they fix the histogram and they just ask for observations of counts in each bin. And then they answer queries. Actually, they not only get counts in each bins, but then they get the individual counts. They also, so they have some redundancy and they use a similar least squares method to refine the answers and get a consistent set of answers out. Okay, there's two other approaches that focus on spatial queries. These are two-dimensional counting queries, typically range queries. And they both use as inspiration a KD tree, which you'll recall is a data-aware hierarchical partition of the space. Typically what you do is you pick one dimension and you choose the median, and then you recurse. You pick the next dimension, and you'll divide each of those two regions according to its median. And you can build a hierarchical structure that way. So these authors, so that structure, the tree of regions would actually look something like that. So the first piece of work that touched on KD trees actually did something what they did was they first got a rough estimate of the database using the Laplace mechanism. So over a 2D grid, they just sample every count. And they get this estimate x prime. Then they use that to build a KD tree, as if it was the true database. But they stop. They have some stopping conditions because they don't want to build a tree that's too deep. So they have some parameters which say, look, if the sum of the counts in the regions are too small, or if the counts are maybe not small but already uniform, I'm not going to split anymore. And then once they have that KD tree, then they get fresh counts for all the regions in the KD tree, and they use those to compute answers to their two-dimensional range queries using another portion of their budget. Okay, that's one KD tree technique. Another one is to do a kind of hybrid structure where the first L level, you build the KD tree from the top down, but only a certain fixed number of levels that you decide on ahead of time. And you use the exponential mechanism to compute the median. Okay, they use a method that was, I think, originally proposed in the pink paper for computing the median. They try a few things, but they decide that that's the best one. And then they stop at depth L, and then they continue with a sort of fixed resolution quad tree for the rest of the levels. They form that, and then they use the rest of their budget. They skew their budget towards getting counts of all the resulting regions, and then derive the workload answers again using least squares because there's some redundancy in the observations.
What are they doing with the median?
The median is for the KD tree. So they need to repeatedly select this in each dimension the median boundary, and they do it in a noisy manner. Okay. So there's another technique which I won't say much about because you'll hear about it tomorrow. I believe Michael Hay will talk about another data-aware technique that tries to optimize relative errors. The observation here is that, well, you'd like more accurate answers on query answers whose magnitude is small. And you can afford more error on query answers whose magnitude is large. But obviously, you don't know the magnitude ahead of time. So what they do is they do multiple rounds. They answer all of their workload queries using the Laplace mechanism with a small portion of their budget, a fraction of their budget. And then they resample the database. They get more measurements. So the naive thing to do would say, OK, I got a noisy answer back about this query, and it looks like a big number, so I can stop. But if it looks like a small number, I'll ask again. But what they do is when they ask subsequent questions, they sample noise carefully from a complicated distribution that simulates the effect of having only asked the question once with a certain epsilon, with a boosted epsilon. So Michael will talk about that tomorrow. The final answers have the same privacy cost as a single Laplace random variable with the resulting error. Okay, so and then we get the multiplicative weights, which I really don't have to say much about because Moritz described, and I guess we'll learn more about this when we see the experiment. So here again, we choose a t and we divide our budget, and we select poorly approximated queries in each round, and we get more information about those queries using the Laplace mechanism. So I think that as far as the data-aware techniques go, this technique has a lot going for it. So if I've got it right, again, Adam, in terms of squared error, the dependence is 1 over epsilon to the 2/3, which is asymptotically better than the workload-aware techniques. Okay, so that's important. And to some extent, the observations, I mean, we might ask, this is clearly a data-aware technique, but we might also ask, to what extent is it workload-aware? So the observations are, in some sense, inherently customized to the workload because they are a subset of the workload. But I think there's a question here that I'd like to learn more about is whether it follows that the right measurements to do are the workload queries themselves, or whether you could measure something else and be more effective. In fact, I think if I understood the paper correctly, there is an instance in which when you evaluate a workload of marginals using this technique, the measurements you take are actually the Fourier coefficients and not the marginals themselves. So which is a point at which these techniques sort of come together, because they're looking for a different set of, you're looking for a different set of observations that could be a better way to go to the database. So I don't know how that seems to be a practical technique, and I don't know how it affects the error bounds and stuff like that. So as far as this technique is reasonably efficient, you do have to compute all the workload queries for every round, so t times. So that's a little bit of a disadvantage. Okay, so representative experimental findings. If you build the data-aware histogram, the authors found that on range queries, the error would be reduced. That's the first technique I proposed, I described here, where you use the variance optimal, try to approximate the variance optimal histograms. They reduced the average per query error by about 20 to 40% compared with using sort of the fixed workload-aware method like wavelet or something like that. The authors, as far as I can tell, the authors found that the KD, these sort of adaptive KD tree techniques did not really outperform the kind of workload-aware quad tree. If you just build a quad tree in 2 dimensions, you get as good performance. So those techniques don't seem to be finding a favorable way of testing the database, a way that's sort of worth it, using your privacy budget in order to test the database to decide on what to ask. And I think Katrina will present her experimental results, and there are cases in practice where the multiplicative weights algorithm outperformed the matrix mechanism by a factor of 10 or more. So in order of magnitude, a very significant improvement. And that's exciting. But I also have to say in defense of our techniques that there are other data sets and other workloads for which the workload-aware techniques still outperform the multiplicative weights techniques. And I think it raises a lot of interesting questions. Some of them I think I have here. So here's the summary. So I mean, it's possible, I think, to get lower error than approach 1 in some cases, and in some sense we should expect this because we're exploiting the database. We have sort of more information in the design of our mechanisms. These techniques that are data aware, I mean, you've noticed that there's a lot of parameters you have to pick. All right, so you have to divide your privacy budget. You have to sometimes choose the number of rounds or heights of trees, different things like that. And I think those parameters have a lot of impact in practice. It's not clear how an analyst, if you deployed these algorithms, how an analyst would pick those parameters. It's also not clear how to get publishable, non-sensitive error rates out of these algorithms if the techniques depend inherently on the data. So it's nice to be able to give an analyst a noisy answer to a query and also say, this is the error rate that you expect. That seems to me an important property of an algorithm that if we're going to deploy these in practice. And then the other question I think is, to what extent are these algorithms really exploiting a specialization to a workload? I think the question I was getting at is that as you shift from workload-aware algorithms where the evaluation is quite simple because it's largely independent of the database, properties of real databases matter a lot. And I think our group is as guilty of this as others, but I think that questions of what do real databases look like are going to become more and more important as we evaluate these techniques in practice. And we may have some arguments about what properties of databases matter, also what properties of workloads matter. So we use very contrived versions of workloads that are either very large structured things like all range queries or random subsets of range queries. And I don't think we know enough about what workloads really appear in practice, what properties they have that we can exploit, and what properties of the data determine error. So, I mean, I think the only thing that's really clear to me at this point is that sparsity has an impact, but sparsity versus density has an impact, but it seems like there's more going on, and so I think there's more to say about that. Okay, so I'm going to wrap up. So we saw these two approaches. I hope it's a helpful categorization of the two approaches, that some solely, they both sort of have these observations that are different than the thing you ultimately want to know. And that seems like an important principle, but they come at the observations in different ways. One solely by analyzing the workload, and the other class of techniques by exploiting the data. They both result in practice in significant improvements in error. So these are just the benefits and limitations that I repeated previously. In terms of open questions, I still think we have more to understand about what makes one workload harder to answer than another. This would come up in practice if you had an analyst who needs to decide whether it's worth thinking carefully about how to specialize their workload with the hope that they will get better error because they've simplified the queries that they want to know. Or can they keep their workload more general and submit it to the mechanism and get almost the same error? That's a practical question I think is kind of important, and it hinges on what makes a workload hard, what makes a database hard to support accurately under these mechanisms. Can we avoid the computational dependence on n, the universe size or the domain size? In the context of the matrix mechanism, hard problem for us was how to make the non-negative least squares work and how to analyze it. And of course, this is a certain class of queries. These are linear queries. They're important in practice, but there's a lot of other queries that these techniques don't necessarily extend to. So obviously, there's lots of questions there. OK, that's it. Salil, yeah.
So a question on the experimental comparison with multiplicative weights.
Yeah.
So I wonder, comment on whether the size of the database makes a big difference there, because at least theoretically in techniques like the multiplicative weights, the error grows if you don't normalize the way, instead of without dividing by the size of the database like Moritz did, but the error grows like square root of the size of the database, and things like the Laplace mechanism and what I understand from the workload-aware mechanism, there is no dependence on the size of the database in your error bound.
Yeah. Yeah, when you say the size of the database, you mean the number of records in the database. Right.
So did
yeah.
something that came out in the experiments, like the cases where one performed better than the other?
Yeah, I mean, and we're still looking at it, but I think, and these folks may have more to say certainly than we do, but I think certainly that's a factor. I mean, this technique is very effective for sparse data. I mean, because it starts with an estimate that is pretty good for sparse data sets, and then it improves it.
So sparse data sets are just a small number of records?
Yeah, small number of records and large regions of the universe in which there are no records. So. Yeah, so that's one factor. I mean, another factor I think we have to be careful of in the experimental evaluation is that, there's a better dependence on epsilon. So if you turn the privacy parameter epsilon down, I think in the limit, this technique will always beat competing techniques. But you have to ask whether either technique is giving results that are useful in practice. I mean, that's a part of the space where we don't want to go anyway. So, but.
Add one more thing to your question, that you can calibrate the number of rounds in multiplicative weights to not the database size, but something small, something independent of the database size. It's not like, if you did this in practice, I don't think we ever choose the number of rounds in such a way that we get square root n or something like that.
Oh, okay.
So it's a good question what it should be in practice, but
Just
Yeah.
to follow up on that, were range queries one of the set of queries where you do much better using?
Well, I think we were looking at the same or similar workload. So I think it was subsets of range, relatively small subsets of range queries, though. Which I think is, but I mean, yeah. So, did you have an insight about the range queries?
There's some geometric intuition. I'll talk about it tomorrow, which
Okay.
sort of says why really range queries are much easier than you can answer them with logarithmic error as you actually show.
Yeah.
But multiplicative weights, at least provably, only has square root in it.
Yeah, okay, okay, great, yeah. Any other questions or comments? Yeah.
At the very beginning of the talk, you mentioned that although what you were calling n
Yeah.
is a large number, you can in fact restrict your attention to a relatively
Yes.
small set of cells in the histogram.
Yeah.
Can you say just like more about that and how you know this and what?
Well, no, it's a very straightforward thing. It's just that let's say I have my domain x1 through x10, and I look at my workload and I realize that there's no query that asks all the queries that touch x1 through x4. They just use the sum of that region, and they never look inside in some sense. Then there's no point in treating the universe as 10 elements. We can shrink those 4 into 1 count. And as far as the workload is concerned, that transformation, that transformation of the domain, doesn't affect anything. It does, in practice, mean that the relationship between the domain size, the universe size, and the database size is changed. So I think in practice, that's why it impacts things. I mean, it's a simple pre-processing step to look at your workload and look at your domain and kind of compress it in this manner. But it also tends to make the database denser. So that's all I was trying to say. I mean, and it's also an argument that I use for when I talk to database audiences, people get upset. Oh, what are you talking about? The universe size is exponential. You can't even represent your database, and how are you going to answer queries and all this stuff? Then kind of one of my only answers is, well, I hope that it may be the case that for workloads that I care about, I can shrink the domain size. I mean, there's other clever things you can do to address this problem where you can try to look at the multiple dimensions. And I think that you guys did this in your implementation, and it's come up for us too. When you have these multidimensional range queries, and you really have sort of like, you can exploit the fact that the workload may be, it's kind of a product over the dimensions, and you can sometimes represent it without enumerating the product of the domain size. You can represent it in a compressed fashion or approximate it, and we've used some tricks like that in the past. So there wasn't a deep insight there, but I think practically these things matter.
I was trying to understand this before this talk, and just in general, I suspect you're probably right that for some reason, when you actually think about questions that are posed, they implicitly end up collapsing a lot of regions, and somebody must